one, ready.
Hello, everybody. My name is Václav Petráš. I usually go with Vašek in the US. And I will tell you today about how we teach tools for open geospatial science, how we do it here at North Carolina State University, where I am at. And first, let me introduce myself and my co-presenters. So, me and also my co-presenter Anna Petrášová, we are currently students at North Carolina State University at the Center for Geospatial Analytics. And here we are focusing on different geospatial topics. One of our flag research is concerned with tangible user interfaces. But our background is actually in an interdisciplinary field, which at our university was called geoinformatics or geomatics. And our advisor is Dr. Helena Mitášová, and she's here at the North Carolina State University, part of the Marine, Earth, and Atmospheric Sciences Department. And we work with people at this department, at the Center for Geospatial Analytics, on different geospatial challenges. And some of these are concerned with processing data or analyzing data and classic geospatial or GIS tasks. And some of these go as deep as developing the code. But ourselves, we are actually not computer scientists, but still with the powers open source can give us, we are actually able to contribute in a reasonable manner into these projects, even without being part of, let's say, computer science department. But now let me focus on today's topic, and that's our course which we developed for teaching open geospatial science. So open science really begins with the first scientific journal, which was called Philosophical Transactions. The first issue was done in 1667, and that was really the idea that the science needs to be shared. So we don't do science anymore just in behind closed doors, but we really want other people to see our scientific result and benefit from them. With that, over time, we formulated the ideas why we are actually doing this publishing. So our goals with publishing are usually registration, so that the scientist who is doing the research gets the credit for the research. We also want to archive the knowledge, preserve it for the future. We also want to disseminate the knowledge so that people can actually make use of that knowledge. And finally, we want to see if this research is worth it. So we do peer review. That works quite well, but now we have a new challenge, which was not here in 1600, and that's the fact that most of the research relies on software. And a lot of people was already thinking about it, and now more and more people are realizing and arguing for the software which is related to research, for that software to be shared. That brings us to open science as we see it today. And several authors describe open science basically with this diagram, which you can see, where on one side we have only the text published, only the scientific paper, but that's all. and that's not really that reproducible. But we want the research to be reproducible. So to do that, we have to publish also all the data, all the code related to the research, and with that also all the versions of these things like code, text, and data, so that we can see how the research developed and we can learn from that as well. The course we are teaching exactly for these reasons, that this is something what now the students need to know. Open science is perhaps not the mainstream at this point, but all seems that it will become mainstream in the future, and we want our students to be prepared for that. So we introduced this course called Tools for Open Geospatial Science, and we are really focusing on some practical tools, mostly software tools, which are used together with other things in open science and specifically in geospatial science. It's a graduate level course here at NCSU Center for Geospatial Analytics, and it's a special topics course, which means that it is kind of experimental, and we did it both on campus and off campus to accommodate different students. And this fall semester, it was the first semester we were teaching it. The course is split into three main areas: the basic open science topics, the geospatial topics, and then advanced topics. And now I will go through all these different parts of what we did with the students in the course. So we started with things which are somehow maybe more familiar with the students and are kind of basics for all the other things. Of course, we wanted to show students how the open source communities works, because that's very similar to how open science ideas or how open science philosophy envisions the science to work. But we can't go straight into how the open source communities works, because they are kind of mysterious and complicated for the students. So we start with things the students know, and one thing the students are familiar with is how papers are published. They usually encounter PDFs or HTMLs of different papers, they read them, sometimes they even write them. So we introduce them to tools which they didn't know. They of course know things like Microsoft Word or Google Documents, but these tools are not really ideal for writing. So we introduced them to two tools, specifically Overleaf and Autoria, which are tools for collaborating online on scientific documents or research papers. Both of these tools are using several concepts which are quite advantageous in general open science. They are using LaTeX and Markdown as their basics or backends to process the text. And here we have the switch of the mindset from something which is purely graphical with a Wysiwyg interface to something which is based on plain text files, which are then interpreted into something which is graphical, which is the final result. So this there is this parallel between this and scripting, for example. This was really game-changing for some students. One student said that learning about LaTeX and Overleaf was, in terms of technology, the most game-changing lecture in his whole college education, that it was the most efficient and mind-changing class he had. So it seems that it was doing what we intended for it to do. Another thing similar to that is versioning of the files. So whatever format you have, you create different versions of the file as you progress in your writing or in your research. And we all have seen things like this, where we have a file, and then the second version of the file is simply the first file name with attached number. And this is, of course, not ideal, and it's not sustainable when we have multiple people contributing to the same file. And for that, there is, of course, solution, and that's revision control systems. And that was another thing we introduced our students to. We specifically worked with Git, but we were also talking about the other revision control tools which are used, like Subversion and Mercurial. And we were showing and practicing how to use that. And for the assignment, what the students did was just very simple thing, and it was changing few lines in a text file, which was then committed to Git. It was very simple because this is the first time students see something like this. It is maybe even the first time students work with plain text files directly. So we were keeping it low and really just introducing them to the concept. Together with Git, there is, of course, GitHub, which is often confused together with Git, and it's not really clear to many people what's the difference. And many of our students heard about Git or GitHub, but they didn't really know what's the difference. So we were trying to address that. We were actually using GitHub since it is really popular, but we were also trying to explain to students what are the challenges and what are the things to consider when they are selecting a platform for sharing the code online. So we were talking about the terms like proprietary and freemium, and of course also about open source licenses. Then in the central part of the course, we focused on the geospatial topics. We, of course, worked with QGIS as the leading open source desktop application, but we were working also with more advanced tools like GDAL and GRASS. And with that, we, of course, had to introduce students to command line. So we were doing a little bit of Linux or Unix-like command line. The thing why we were actually focusing on the command line is that when we think about geospatial workflows, we usually tend to think about geospatial workflows as something really visual. And that's really how our students are trained as well, that they use the graphical user interfaces, they look at the data constantly, and in the graphical user interface, they, with point and click, they find all these tools they want to use, and then they fill in dialogues and press the run button, and then they get the result. This is all good, but once you want to record that workflow, the question is what you do. So, of course, what happens is that when this is the only thing you know, you record something visual again, and you record screenshots of the interface. But these screenshots, they of course may be very different for different versions of the software. They are very difficult to edit when you realize that there was some mistake made, and it's even not guaranteed that it will be same on different operating systems. So of course there is a smarter way, and that's scripting. Here the 3 lines we are looking at are the code for the same thing we have seen on these previous 3 screenshots, but each of these lines is in different scripting language, and you can also see that they are actually fairly similar. And there is many different choices in scripting languages. In the class, we were using mostly Python and Bash, or not really Bash, but just really the Unix like command line. And it is important to know that we are not really teaching students scripting or programming even. That's really part of a separate course, and it's appropriate to have it in a large full course. Here we were just touching on it and emphasizing the ties to open science and to other tools which are used in open science. And then in the final part of the course, we were focusing on these more advanced topics. So of course we have the scripting, but now there is this new concept of computational notebooks, which is not that new if you consider all the computer science history behind it, but for researchers this concept is really new, and the concept is combining text, code, and figures into one document. It is applicable to not only all scripting languages, but basically all other languages as well. But we just focused on one thing, and that was Python and Jupyter notebooks. But there are other things like R Markdown, or even some more advanced things like Emacs or Org mode. The idea was, again, not to find out every feature which you can find in Jupyter Notebook, but really just, again, introduce just the concept of that to the students, so they know that something like this exists and they are able to use it for their own work. When we have something like a code, script, or even the computation notebook, we of course want to publish it. And we already talked about GitHub and other publishing platforms for code repositories. But with our students, we didn't only talk about how to technically put it online, but we also talked about how to publish the code in the relation to a paper or in a relation to an open source project. What things to include, like that you should include a README file or some kind of documentation for your code so that people know what it is and how to work with that. And also that it is important to license the code. So we were talking actually about the different open source licenses, how to navigate through them, and which tools to use to choose an open source license. You may have heard that there are pages like chooselicense.com, and there is also a classic list from Free Software Foundation and Open Source Foundation initiative, where we have a list of approved open source licenses for different uses. I keep saying open source, and of course, you know that in Geospatial we often say free and open source software, and also we can say free, libre, and open source software, or just free software. We actually made these distinctions with students and discussed why these different terms are used, and that was really a good tie with the licenses, which of course are quite difficult to teach if you are not on a law school. One way how to publish the project or the code is to make it part of a bigger project. This seems a little bit more difficult than just publish it, let's say, on GitHub in one repository, couple of files. That sounds very simple, and that's what we were practicing with the students. But we also told them about why they may want to consider including their code into some larger project. We discussed about the benefits of it and also the challenges. If you have never done something like that, you may want to know that there is a couple of things you have to consider when creating a project. You don't want to unnecessarily duplicate others people's effort. You don't want to develop your own interfaces, whether it's graphical or command line interfaces, and you want to really reuse what's there. So we were talking about that. And there is, of course, a couple of options you can work with or try. Is there you can publish an R package, Python package, you can publish a GraphJS module, QGIS plugin, and all these options, they have different level of integration into the project and different complexity of how this is done. And of course, there are always some risks involved in how the code will be preserved in the long term. And for that, there is literature, and there is also a lot of experience with from people on the mailing lists. So that's something we were discussing as well. To really make it more real for the students, we were trying to use as many examples as possible for this concept of publishing your code as part of an open source project. We use this futures model, which is a model our lab is working on. And it is an urban landscape pattern simulation. And it's really a typical example of computational research. Our group did an implementation of that model as a GraphJS add-on. Originally, it was just a standalone C code, which was very difficult to run. And we exactly did this integration part. So we were discussing all the aspects of it, how the source code is managed, specifically for the GraphJS add-ons, how the history of these modules can be accessed, and also where the documentation goes and how to write the documentation in a way that it can be consumed by these automated tools and turned into a website. And we also discussed this idea that you can actually get a graphical user interface if you do the right integration with the right tool. With all these things we were doing, the notebooks, the command line tools, and many other tools we tried, some students were installing it on their computers, some students were installing it on virtual machines with Linux. And by the end of the course, they had a lot of experience and also even bad or challenging experiences with getting all these tools to work together. And that's, of course, something what we encounter every day. And that's something which is a challenge for open science as well, because when we publish some code, some procedure, it has all these dependencies, all these environmental settings, all these files and file structures which it expects. And without that, it won't run and it won't reproduce the results. There are fortunately solutions for that, and that's what we were doing with the students at the end of our course. We were talking about these environments like Docker, Vagrant, and virtual machines, which can allow you to pack your environment into something which is manageable. And for example, in case of Docker, what we are looking at is a Docker file where we, in a plain text format, we specify what are the individual dependencies of our code. And then Docker, the software, is able to create something which is called an image or a container when it is running, and that is then used to execute your code in a self-contained environment. So at that time when we are doing it, it's something which is a challenging concept, but when you hear about it for the first time, but at the same time, the students had a high enough motivation to understand why would they do something like that. And then finally, in the final lecture, we focused on how to put all these different pieces together, because we are talking about the file formats, we are talking about scripting, about revision control systems, about publishing code and these environments. So we had one specific lecture just about how these pieces of the puzzle fit together. You can see the overview on your screen, where a concept of a new open science research publication contains things like text, which is what we would understand under journal paper. But there is, of course, also data, and then there is code, which we even split into two parts, into reusable code and specific code. And the reusable code is the general code, which is implemented in a general way, something which can be used in the future by other scientists with different data. And that would be the case of the futures model, which I was showing. But then we have also the specific code, which is something which is associated uniquely with the given research publication, which is using the specific data set. And it's really there to enable the reproducibility of the results represented or presented in the paper. And for that code to run, we have the environment, like the Docker file I was showing. And then finally, all these things are managed in something like Git. So multiple people can work on it. And also we have exact version numbers for each different change we did. Again, we were looking at a specific example with our students. It is a paper which I published and was using all these different tools to enable reproducibility and also enable reuse in the future. So the assignment for this class, for the students, was actually to reproduce this paper and tell us how easy or hard it was to reproduce paper like this. We don't know what the students will say, because that was an assignment from last week. So what the students actually will take from the course, or what we hope the students take from the course. We want them to be able to use the skills they have, to use them for publishing papers, but also for making more efficient workflows in their lab or in their individual research. We want them to be able to publish a script with their next paper. We want them to be able to manage source code or even some other files using Git and perhaps GitHub or some other platform. We want them to be able to use tools like Overleaf to create scientific texts, or maybe even to generate reports automatically using Python. We want them to be familiar with Jupyter notebooks and be able to use them, maybe even for assignments. It doesn't have to be for paper. And we also want them to be able to navigate through this landscape of different open source projects, how to choose in between them, how to be plugged into the communities, and how to use it for sharing the research. The course itself was also using many of these tools we were teaching in the course. we were using HTML and restructured text to write all the course material. We do some conversions of the formats using scripting. We have all the course material in Git. It's actually hosted on GitHub, including the website. And the lectures for the course are actually also in HTML in an open format. If you are more interested in why we have chosen these specific things, you can see a reference for it on the screen, and you will have access to the slides after the webinar as well. All the course material is actually also open. So we follow the idea of openness through, and you can get all the course material in form of website. You can get the lecture slides. You can get also the original raw plain text files. And for each of the topics, for each of the weeks, we have an assignment, and the text for the assignment is published as well. And all the recordings from the class which we are able to make are also available. And we even share the promotional materials we used here at our university to promote the class. We actually do the same for all courses from our Geo for All lab here at NC State, so we can get that as well. And with that, I will just point you to the other resources we have. You can see the URL for the, or short URL for the course website, and also the URL for our Geo for All lab here at NC State. With that, I will thank you for your attention, and I will turn it to Rafael to lead the discussion for the remainder of our time. Thank you.
Hi, Vaclav. Thank you very much for that presentation. Very interesting. So everyone, if you want to use your microphone to ask questions or comments, you can roll the mouse to the bottom of the interface for the webinar, and a menu will pop up, and you can turn on your microphone on the lower left. So we have a chat here. We have a quick question while there is some other questions. Is I have to go, but I want to watch the rest. This is really great. North Carolina State's nice work. So you might want to investigate the Open Science Framework Cloud System, OSF.io, which is cloud platform to support open science. I think it has a GitHub add-on and has a wiki communication system. The question I have is, can we get two labs collaborated in this way in some area of geospatial science? That's from Charlie. Sure.
Yeah, okay, so thank you. Yeah, the Open Science Framework, that's a good tip. We actually are already using it. We were talking about it in the class. We didn't have a special lecture just for that, mostly because of the limited time and all the tools we wanted to cover. But our group is using Open Science Framework. We are quite satisfied with it. The Tangible Landscape project, for example, has very strong presence on the Open Science Framework. We exactly use the tools which you mentioned. We have our GitHub repositories linked there, and that's really something which was important for us actually, to be able to use the Open Science Framework. So we can keep using the tools we want to use. And I think that's one of the things Open Science Framework people are highlighting, that you can combine it with the tools you are used to using, including actually things like Google Drive, which are, let's say, not typical open science tools. How the labs can collaborate? I would say that's much more difficult question, but things like the Open Science Framework is really something which can facilitate that. And with that, I think it's important to realize that the collaboration, at least from what I have seen, is usually, it all works best when it is based around some common project with some common goal. So it's hard to just get collaboration without this project or a common goal. So what we have a lot of experience with is collaborating on GrassGIS, which we all people in our lab are collaborating on in a long term, and that's really something where multiple people from different institutions, not only Geo4 or labs, are collaborating on, because all of those people have some interest in GrassGIS being developed, and we are interested in using GrassGIS for our benefit, and so we have also benefits when we share our research through GrassGIS. The project we have started, Tangible Landscape, we are trying to create the same kind of environment. We of course have the code on GitHub, where anybody can do a pull request. That's the currently common way of contributing in open source. And for that we are just basically copying what works really well in the open source world, where you have the code base, anybody can access it, and when they have an idea, they implement it and push it back. And then somebody is the manager. In case of Tangible Landscape, that's us, where we can say, well, this is a good change. No, maybe this change needs a little bit of more development, and then we can make it part of the project. And that's really something where we can very easily start collaborating right away without any official requirements. You do the work, and you don't have to ask for permission to actually do it.
Great, thank you very much for that. So everyone, if you have any other questions or comments, feel free to turn on your microphone or to type them in the chat. Again, roll down your mouse to the bottom of the interface and the menu will pop up. Well, while we get some question or comment, I want to make a quick comment. I'm so glad you touched on this subject, because it is a very important complement to the other webinars that we've been having, in which we have concentrated more on technologies, applications, or doing it locally, analysis. But then this is very interesting, the how can we cooperate and collaborate remotely and produce good products. I think it was a very useful information.
Yeah, and of course, I already said that actually during the webinar. We have all our courses, which our group is doing. And when I say our group, what I mean is NCSU, Geo4, or Lab. All these courses, past and present, are linked from our website, and the links most often times go to a website where at the bottom you can get a link to GitHub, where you can get the raw materials. And even if you are not familiar with GitHub or the coders way of doing things, you can actually still use GitHub without too much hassle. There is a download link to download the whole repository as a zip file. I actually use it sometimes as well when I just don't want to clone the whole repository and I just want the latest snapshot. So you can do that, and you can even edit the files on GitHub itself if that's something you want to do. So you don't need to even have the source code on your own computer. You just use the web interface. So I think that's also opening this platform for people who are not considering themselves as somebody who is a coder or people who are not comfortable with doing it through code on their computer.
All right. So, okay, I have another question. Have you had experience working in this way, as you described, with international partners?
We haven't worked with anybody on the course material yet. We are getting some feedback here and there, but we have a lot of experience with the GrassJS community, which is international, and we are using GrassJS as a really a platform where we can publish our research. So when we have something we want to publish, we put it there, and then of course the question is if somebody wants to pick it up and change it. So far with this, for example, of this futures model, we had people using it and giving us feedback about our tutorials, how to use it, and about their struggles or technical issues they encountered. We didn't have really people sending us back some corrections of the code, but we have seen this happening in the GrassJS community in general. We have seen people submitting tickets or writing to mailing list that they found a discrepancy in between the code and the equation which is written in the documentation, and they were suggesting which is the change. Then there was a discussion about what references to use and what's the trustworthy equation for that particular model or computation in question. And all these discussions were, of course, happening on a public mailing list, which is completely international.
Great, great. All right. Again, if there is any other questions or comments, feel free to turn on your microphone or type it in the chat that is on the menu at the bottom. We're here.
Hello, can I ask a question then, please?
Yes, please go ahead.
This is Lee Hatchadorian at Temple University. So I have used, I have had some of my students in some classes, I've required them to do their work in Markdown, which I use a lot and want to get them using more. I've been a little more reticent to try to push them towards using GitHub, which a lot of them have not yet been exposed to. The ones that are interested start using it anyway, and it's kind of a heavy lift to bring into a course that's not entirely focused on this. But I wonder, the thing that I think could make this work is if it gets more adopted across a range of courses in a department. And so what I wonder is, at your lab and in your experience then, are other professors in other courses saying, okay, now give me your work in Markdown, or submit all your assignments via GitHub, or then when they've taken this course, are they like next semester going to say, okay, you took open geospatial science last term, do all your work in LaTeX or do all your work in Markdown?
Yeah, so I will try to unpack several of the things from what you said. I really like what you touched on. One thing with that it is hard to introduce some things like GitHub into other class. Markdown is maybe kind of very simple. That's the idea, and it's easy to make it part of a class. Basically, the reason for why we actually developed this course was that as we are thinking about it, and we are thinking, oh, this tool maybe could be part of this class, and this tool may be part of this class or this assignment, we realized that we are not able to efficiently spread all these tools to all these different classes because either we wouldn't just do enough or we would overwhelm the other classes. So that's basically how we came up with having a separate class just for the tools for open geospatial science. So it's not just pure let's say, motivation or practices of science, like in terms of scientific method. It's really focusing on the individual tools, and it's really about all these open science tools as a separate subject. So we can actually touch on all of those. As I was saying, we were not really going deep into each of those, but we had a week to talk about Git, GitHub, and try, things like that. With applying this in other courses, ask me maybe in a year when we will have actually students who had the course, and we will also communicate enough about this course with all our colleagues here. But what is happening at the Center for Geospatial Analytics already is that we have different courses which are using different software tools to do the same type of analysis. One very famous course which is doing this in a very rigorous way is the one which Dr. Mitasheva is teaching, and that's the Geospatial Modeling course, where we focus on a lot of spatial analysis, and the lectures are really strictly software independent. It's really the theory without any software implementation details, but the assignments students need to do in both Grass.js and ArcGIS. Leaving on the side the choice of these two, the idea is that there are two different software packages, and the students need to generalize their ideas about the specific analysis and work with the two software packages, which may be different in all these individual parts. Of course, with having this course in their portfolio, they are able to benefit more from the things like Grass.js, where they have a choice of using either the graphical user interface or the command line interface. And if they use the command line interface, maybe after taking this open science course, they are going to be more efficient in this in the part of this class. But as a requirement, I have seen it in my undergrads, where we had professors which didn't maybe require reports to be delivered in LaTeX, but they were giving extra points for that because they were saying, well, it's something you should know and it's beneficial in the long run, but I know that like you have to learn it, so I'm going to give you extra points. That was working quite well. We are not doing it here as far as I know, but it's one way how to do it. I guess that's all I have in mind for it at this point.
All right, thank you, Lee, for that question. Again, we have a few more minutes if anybody has another question or comment. Yeah, I think that was an interesting point, because sometimes students feel overwhelmed with too many options, but I'm glad that you have been working with this approach for a while and you are being successful. So that's very interesting.
Yeah, we have several students who in this course who either themselves came with that or agreed with when we were discussing it, that this course is something it shouldn't be a graduate or even PhD level course, which is basically how they were taking it. They were mostly at the end of their studies, when they realized that they need all these tools to actually be efficient. That it would be much better for them to have this course when they started, or even in their undergrads, to actually benefit from all these tools while they are doing all the research and all the other classes. So plugging this into the whole curriculum and whole career development is something which is still ahead of us, I think, and something we need to work here at NC State and also in general, I think we are not clear how to do it.
Great, great. All right, one more time, if anybody has a question, you can turn on your mic or type it on the chat. If not, we're getting close to the time limit.
Vaklav, this is Sujit. Thank you for your excellent presentation. Very interesting. It's just an observation, really. Following up from Charlie's suggestion on how we look at ideas for linking collaborative work. And I was thinking, we have, for example, you talked about graphs, and there is this summer of code activities and all these kind of existing activities happening. Can we make use of, in your mind, do you think, is there any kind of existing initiatives we can build upon to make use of this kind of ideas?
Well, we are definitely taking use of the Google Summer of Code. We had this year, we had 2 students who were which we were mentoring, and they were working on Google Summer of Code. But right away, I don't see how this would be helpful in collaboration. One thing which was tried and we have experience with is that if you see somebody working on the Google Summer of Code, then you know that it is the student who might be your next PhD student or your next postdoc, right? That's something you are interested in.
Okay, got it.
But things like Google Summer of Code are really individual in the sense of the individual student is the one who is getting the financing, and that's ultimately what decides. But the mentoring can be done by somebody else. So now we were mentoring people who were in our lab, and it's maybe the simplest way what you can or simplest thing you can do. But in the past, we were actually mentoring people in a different lab, in the Geo4All lab in Prague at Czech Technical University, where we have connection because that's where we did our undergrads.
Oh, I see. Oh, interesting. Thank you, Vaklav. I see one question from Micha in the chat window. So thanks again for your answering. But the Micha's question is in the chat window. Rafael, do you want to read it out, please?
I'm sorry, didn't hear you. What did you say?
Micha has sent a question in the chat window. Thanks for the presentation. What is the advantage of OpenLeaf compared to just putting text files in a Git repository? It was from Micha. She put it in there is a question in the chat window, if I understand.
Yeah, we can see it here. Again, what's the advantage of OpenLeaf compared to just putting text files on a Git repository?
So the Overleaf platform, that's a partially open source, partially proprietary platform, which has this freemium model where certain features are for free and certain you have to pay for. But how it works is that you can edit the things online, and there is this moderately advanced, let's say, LaTeX editor where you can edit LaTeX code, and at the same time, without pressing any buttons or anything, you get resulting code, resulting PDF document on the site. You can do the same thing on your computer, but you have to install LaTeX, and to have it in a cloud, you have to do some extra thing, like putting it to GitHub or Git and GitHub. And that's all possible, but it's a hurdle for many people to use LaTeX, although it can give them a lot of advantages. So Overleaf really removes this barrier, but at the same time, one of the reasons we are teaching it is that you can actually use Git together with Overleaf. So at the same time, you can interactively in a, like this Google Documents style, work on it in your web browser. But then when you want to do it on your computer, let's say maybe generate automatically some figures for the paper or some tables, you can clone a Git repository on your computer and work there. So you can really combine the desktop and web approach with Overleaf. And it's very seamless because the Overleaf is using LaTeX as a backend. So that's something which is very reproducible, very clear what it is. LaTeX itself is, of course, open source. So you can have the very same thing which is in this cloud, which potentially is closed, but you have this, exactly the same thing on your computer, fully open, and you can anytime leave the cloud. And that's actually something which is relatively uncommon concept, a cloud which the user can very easily leave. So that's actually something which we also discussed with the students as something which needs to be considered with the cloud platforms, is how difficult it is to leave the platform and reproduce this thing somewhere else, in this case on your computer.
Great. Yeah, thank you, Suchi, for pointing that out, the question. Excellent. So we are right on time for finishing the webinar. Thank you so much for your attendance and your attention. Václav and Anna and Helena, thank you so much for this great presentation, very interesting. And as usual, we will post the recording in the Geo for All YouTube channel shortly. And again, we appreciate your time, those of you attending, and your great presentation, Václav.
Thank you.
Thank you, everyone.